Hey, welcome to Algebra Today. Today we have a special guest star, and it's right here. No, this is not the special guest star. This is what attracts the special guest star, because this is the favorite thing in the world. Favorite thing in the world for the kitty. Come here. Come here. Come here. This is Tinkerbell. This is Tinkerbell, and this is her favorite thing in the world. She loves her brush. She loves her brush. So I told her if she'd come on the show today, and then she could have a little brushing time, which she just absolutely loves. But yeah, her name is Tinkerbell. She's an old grumpy kitty. She's going to turn, well, she's older than some of you guys, actually. Older than most of you. She will turn 16 this summer. So she's going to be getting her driver's license. So watch out for that. But she does love her brush. But she thought she would come by and just see all the algebra folks. She loves irrational numbers because half of what she says doesn't make sense. So irrational is her thing. But anyway, Tink stopping by. Her nickname's Tink or Nuggets, which is really short for butt nuggets is what we call her. But anyway, here, all right, kitty, you gotta get out of the way because we got some work to do. We got some work to do. All right, so let's go to our ladybug. Oh wait, that's not gonna work there. Hey, this is okay. All right, now you're a problem because your brush is over here. See, she's trying to be near the brush. Okay, thank you very much for helping us with our lesson. Let's put this on the floor, and you can kind of self-medicate yourself on that or whatever happens here. She's a handful sometimes, but she tolerates us, I guess that's the best way to say that. All right, sums and products of rational and irrational numbers. We're going to look at that today. We are moving right on. Lesson 21. About to wrap up quadratics. About to wrap up the year. Man, we are moving right on. What is happening? Operations on integers. Here are some examples of integers. All right, integers, positive and negative whole numbers. These are the numbers we're used to. We like integers. Negative 25, negative 10, negative 2, negative 1, 0, 5, 9, 40. These are all just integers. So let's experiment with adding any two numbers on our list. Did she knock us out of focus? We're still good. All right. Any two numbers on our list, or other integers, if we want to pick some other integers to try, and try to find one or more examples of two integers that add up to another integer. Think we can do that? Let's see. Negative 25 plus 40. That's 15. That's an integer. Negative 2 plus 5. That's 3. That's an integer. 0 plus 5. That's 5. That's an integer. 5 plus 9 is 14. All of these are going to be integers. All of them, right? Every time we add an integer to another integer, we get an integer. That's just how that works. That's wonderful. How about add up to a number that's not an integer? Don't know that I can do that because every one I tried, all of these. What if we use something that weren't there? Negative 3 and positive 3. No, that adds up to 0, so that's still an integer. Negative 25 and 100. No, that's still an integer. Can't do it. Cannot add two integers together and not end up with an integer, even if it's not on this list. All right, let's try this instead. All right, let's experiment with multiplying any two numbers from the list, or again, any other integers, and try to find one or more examples of two integers that multiply to make another integer. Okay, so negative 2 times negative 1. That's negative times negative. That's positive 2. That's an integer. Hey, that works. That works. How about 0 times 40? That's 0. That works. Negative 25 times negative 1. That's positive 25. Okay, that works. 40 times negative 10, negative 400. Well, it looks like all of these will again. All right, all of those will multiply together and be an integer. How about multiply to make a number that's not an integer? I know it's not any of those because every one we're trying, 9 times negative 2, that's negative 18, that's an integer. Negative 33 times 2, that's negative 66, that's still an integer. Doesn't work. Integers always end up with integers, whether we add them, whether we multiply them, it doesn't matter, right? Doesn't matter. We can't find anything else that's going to work in different directions. So let's go over here. How you doing there, kitty? All right, she's just watching. I don't know. Let's look at these sums and products of rational numbers in another way. All right, so here's a few examples of adding two rational numbers. Not integers necessarily, although integers are rational numbers. Is each sum a rational number? So just rational numbers, adding them together. If we add 4 plus 0.175, that's an integer because it terminates. It's not a continuing decimal that's rounded. It's terminating 0.175. If we add those together, we get 4.175. Is that an integer? I'm sorry. Is that rational? It's not an integer. Is it rational? Yes, that's rational. Is it a rational number? Yes, rational. How about 1/2 plus 4/5? Remember, to add fractions, you have to come up with a common denominator. So 1/2 is the same as 5/10, and 4/5 is the same as 8/10. So when we add those together, we would get 5 plus 8, 13/10. So over 1, because 10/10 is the same as 1. 1 and 3/10 are 13/10. And that's still rational, because a rational number is any number that we can write as a fraction using integers. And 13 and 10 are both integers. So that is rational. Yeah, that works. Negative 0.75 plus 14/8. Oh, decimals and fractions together. Does that work? Sure, we can just make the decimal into a fraction. Negative 0.75 is the same as negative 6/8, because 0.75 is 3/4 out of a dollar, right? 75 cents out of a dollar, 3/4. It's 3/4. And 3/4 is the same thing as 6/8. If we make it in eighths, since this is in eighths, we need our fraction to be in eighths. But ours is negative because we're negative 0.7. So negative 6/8 plus 14/8. Negative 6 plus 14 is 8/8. That equals 1. That's definitely a rational number. So these are all rational numbers and end up with a rational number. Okay, so let's say a is an integer. Okay, any integer. We had a list of those in the first page. Pick one you like. Make your own. 2/3 plus whatever a is that you decide to be over 15. So we need to make both of these 15ths. So we need 5 times 3 and 5 times 2 to make 10 15ths. So 15 stays on the bottom, adding them together. 10 plus a. 10 plus a. Guess it doesn't really matter what a is, right? What integer you chose. Because on the first page we saw if we add two integers together, regardless of what integer they're always going to be an integer. So this is going to be an integer over an integer, which is a rational number, fraction. So that is always, when we add two rational numbers, we get a rational number. That worked in all these examples. All right, so here's a way to explain why. Why is the sum of two rational numbers always rational? All right, let's suppose a, b, and c, d are fractions. And that means a, b, c, d are integers. If we're talking about rational numbers, they have to be integers. And b and d are not 0. Why are not b and d 0? Because those are on bottom. If you have 0 on the bottom, it means you're dividing by 0. That's when the world explodes or something. You cannot divide by 0. That is, your calculator will tell you error every time. It is not mathematically logical. We can't divide something by nothing. It just doesn't work that way. A and C, however, could be zeros, right? We could have 0 over 7. That just equals 0. So that's fine to have A or C. So let's find the sum of A, B, and C, D and show your reasoning. So if we're going to add those, we would need a common denominator, B and D, if they're not the same, so we could multiply them by each other. We're looking for a common denominator of BD, because if we multiply them by each other, we'll have the same denominator. So this would be on top AD, because we have to multiply the whole thing by D, D over D, multiply it by 1. This we'd multiply both things by B, so it's CB, and add those together. So that would give us AD plus CB, or BC if you want to put them in alphabetical order, over BD. So in the sum, so what it adds together to be, are the numerator and the denominator integers. Because if they're integers, it ends up a rational number. Well, A times D, multiplying two integers together. Well, we saw on the first page, that's always another integer. So multiplying AD ends up with an integer. Same thing CB, same thing with BD. Those are all integers being multiplied by other integers. They're going to be integers. And this is on the top, we're adding two integers. Well, we also saw that that always is a rational number. So if we multiply two rational numbers, which are integers, we get a rational number. And if we add those together, we get a rational number and divide by rational. So that's going to be a rational number regardless of what A, B, C, and D are. So we've already shown that it's always a rational number. So use your responses to explain why the sum of AB plus CD is a rational number. Because as we've seen, if we add integers or multiply integers, we always end up with other integers. And since integers are rational numbers, there's no way that cannot be rational. So that's why the sum of any two rational numbers, and all numbers can be written as a fraction. 7 written as a fraction is 7 over 1. 7 divided by 1. 7 over 1. So all numbers can be written as a fraction. And so all rational numbers end up with other rational numbers when we add them together. So use the same reasoning in the previous question. Explain why the product must be rational. Well, if we multiplied AC times BD, A times C is AC, B times D. When you multiply fractions, you just multiply across tops, multiply across the bottoms. AB times CD is AC over BD. Again, we've got two integers, which are rational numbers. Multiplied together, they're going to end up with an integer, which is a rational number, divided by another rational number integer. So, again, must be rational, multiplying or adding rational numbers. And that works for any numbers because we've just left those variables, A, B, C, D. We can make that any number we want it to. Any rational number. All right, sums and products of rational and irrational numbers. So here's a way to explain why the square root of 2 plus 1/9 is irrational. The square root of 2, we talked about in previous lessons. The square root of 2 is not a rational number because if we convert that to a decimal, it keeps going. We have to round it at some point. It would be a rounded decimal. It's not a repeating decimal. It's not a terminating decimal where it just goes so many and stops. It's a long decimal. So this is not rational. This is irrational, and this is rational. So we're trying to explain why an irrational plus a rational number is going to be irrational. Okay, let's see. So let S be the sum of square root of 2 and 1/9. So S equals the square root of 2 plus 1/9, which is what we're trying to determine up here. And let's suppose it's rational. All right, this is one thing that you do sometimes in proofs in mathematics. It's like we're going to suppose it's rational. All right, so we're going to go with that assumption in our head. This is rational. All right, so would S plus negative 1/9 be rational or irrational? Well, if we've said S is rational, and we're adding negative 1/9. Negative 1/9 it's a rational number, right? It's irrational because it's an integer over an integer, negative 1/9. So if we added a rational number to a rational number, that would be rational. That would be rational because we know, we've already seen, we've proven rational plus rational is rational. So it would be rational. Evaluate S plus negative 1/9. So evaluate, that means actually solve it. So S is this, and if we have the square root of 2 plus 1/9, which is what S is, and we are going to add a negative 9th. Negative 1/9. Well, what's 1/9 plus a negative 1/9? Well, that's 0, so that goes away. So this just equals the square root of negative 2, which is irrational. The square root of negative 2 is irrational. So it becomes the square root of negative 2, and that's an irrational. So we have to use our responses as to explain why S cannot be a rational number, and therefore square root of 2 plus 1/9 cannot be rational. Well, here's what it is. Up here, assuming it's rational, our answer was rational. And then here when we solved it, it was irrational. So so the square root of 2 plus 1/9 cannot be both rational and irrational. It can't be both. It has to be one or the other. There's no way you can be a rational number and an irrational number at the same time. There's no gray area. right? It's like has to be. So if it can't be rational and irrational at the same time, then it cannot be rational, because we did show it's irrational. So irrational because it can't be both. So use the same reasoning as in the earlier question. Explain times 1/9 is irrational. Okay, so let's assume that this is rational, just like we did before. And if we took that, and let's call that S again, and we multiplied it by 9, right? Is 9 irrational? Sure, it's an integer. So if we multiply a rational number times a rational, we get a rational number. But what if we actually solve this? Let's see, what is the square root of 2 times 1/9 times 9? What is 1/9 times 9? That's 9/9, right? We have 9 1/9. Well, 9 over 9 is 1. So that would just be the square root of 2 times 1. So that's the square root of 2. We're back where we were the first time with addition. The square root of 2 is irrational. So it cannot be rational and irrational at the same time. We're doing some pretty deep mathematical thinking today. Not a bad thing. Kind of getting us ready for geometry, kind of getting us ready for higher math. We have to do some reasoning, some thinking. Geometry does some proofs. This is sort of a proof. This is a form of a proof, to where you assume something and then you work it to prove that it cannot be true. So you prove something by using a counterexample. That's what we kind of did. We showed that we assumed it was rational, then we proved it couldn't be. We used a counterexample to show it's irrational. So good preparation. We'll have some problems today talking about rational, irrational numbers, some practice over some things that we've been doing over these type of numbers. So that'll be enough for today. We'll pick this up next time, find something else to explore, and kind of get us ready for next year at the same time while we're wrapping up what we've learned here. So do work and be proud of, and I'm going to find where the cat went. She's around there somewhere. Have a good day.